iets dergelijks. Jullie lezen natuurlijk allemaal over de Bastard Operator from Hell, nietwaar? Daar lees je hem voor. Maar afgelopen donderdag hadden ze toevallig een stuk over een onderzoek van IDC. En de titel was Cloud Repatriation Officially a Trend for Specific Workloads. Wat we altijd al voorspeld hebben, nietwaar? Maar dat blijkt dus inderdaad ook zo te zijn. De redenen... Oh, sorry, I'll do it in English. The reasons: cost overruns, performance and latency issues, and compliance issues. And for system administrators, there's the greater operational control, having workloads on your own specific hardware. Not very surprising, but yeah, this is what we always said, didn't we? Anyway, Nick adds another reason. He's an advocate for a sustainable green cloud. And he, or better his startup, Green Compute, is living the talk. In this session, Nick Hooijberg will tell you what problems he accosted in building a sustainable cloud unit and what solutions he envisages. Nick, the floor is yours.
So, can you hear me? Great. So yeah, thank you for being here today and being interested in this talk. We're going to talk about how to build your own sustainable data center or own sustainable cloud unit, but also the lessons learned. Well, we are a startup now for 1.5 years, and we learned a lot in this journey, and that's what I would like to share. Hopefully it will be useful to you. It will be amazing. So, I don't know if I'm in front of the slide. So basically, who am I? Well, my name is Nick, electrical and IT engineer, also entrepreneur. I like to build and fix solutions, real-life solutions that makes the world better. My hobbies: electronics, low-level C assembler, also Morse code. Those are the things that when I have spare time, which is not a lot lately, but. Why not? If you work, why not towards a future where everyone benefits? That's something I live by. Today we're going to talk about technology, but also that's more a question: how do things work? But some people might be interested in why you want to do this. So I will dedicate one slide to the question why, and then the next slides will be all about how and the technical details. So now we have large hyperscalers that are placed at one central place. There's some cons. So kind of vendor lock-ins. If you use a specific service, it's hard to move to another vendor, or to another cloud. That's quite difficult sometimes. So the EU is having an EcoFET program where they try to develop software that will facilitate a cloud that is like vendor-less in a way that you can move between clouds without changing your software. So that's great. But that's a little bit of a con of the current systems. And also net congestion, because you have on one place you have a lot of energy and then a lot of heat is produced. So that causes net congestion. So the cables, electricity cables have a certain capacity, and when you need a lot of energy, there's a limit on how much you can move through the cables. And also a server is basically a heater. If you put 1 kilowatt of energy in a server, it will produce 1 kilowatt of heat. That's basically the same, only heaters don't compute. So everywhere in the world or in a place where electricity is used for heating, you could apply a server that does the same thing, consume heat, consume energy, produce heat, and also do something useful, computing. So, and it is, transparency control about hardware you mentioned, but also it's a large investment. So, if I would ask somebody, do you want to start your own cloud? It's like, crazy, you need 2 billion. Or yeah, a lot of money to do so. And why is that? Can't we change something like this? So, but there's also benefits, like as a service, it's great that you can, yeah, use something, don't have to think about the implementation of the hardware stack or the software stack, and the maintenance. If you have everything in one place, if something fails, you have engineers who can replace it. So what we try to do with the cloud unit is take all the pros of the centralized system and eliminate all the cons of the centralized system. So, and it is what enables that, that's the cloud unit, aka cloud-led model integrated sustainable data center. That's from Europe, the concept. It's a similar to cloud unit, but it's a building block to build the next-gen cloud. And some properties of the next-gen cloud, that it's secure, reliable, green, sustainable, but also standalone and decentralized. And yeah, instead of centralized, decentralized, now you can say like, there is a spot in the Netherlands where there is a lot of green energy and the heat can be reused. So let's place there a couple of units. So you can spread it all around the Netherlands and use energy twice. So it's more sustainable. Yeah, let's proceed with the how. Like this is what we had a year ago. It's basically a cloud unit, so it's a container. There's insulation around it, so the heat is trapped, but also secured with bolts, so it's hermetically sealed, so no water or air comes into it, and it's using immersion cooling. So basically, that's the diagram. You have your office, your cloud unit. Cold water comes from the office or factory, greenhouse, you name it. It goes to the cloud unit. It's heated. The hot water returns, and there's a connection with fiber and electricity. And if there's local energy, we're going to use that. But if there isn't, we're going to lose green energy from the grid. And we're trying to maximize the local green energy usage. So electricity does not have to travel a lot around the Netherlands. Yeah, and if you have any questions, please ask. So yeah, I've divided the presentation up in 6 pieces, and they're like standalone. So if you talk about security, you can apply this at your data center. Or if you talk about cooling, even if one of them is useful, you can use it on your own. But if you apply them all, then you basically have a cloud unit. So let's start with the first one, the physical security. Thank you, GPT chat, for this. So, the red box, that's the insulation and the outer shell of the cloud unit. Then you want to have reinforced concrete because you need to be certified. If people want to steal your hardware, you want to make it as difficult as possible. And why put it in the ground? Because in the ground it almost never freezes. In the summer it doesn't freeze, and in the winter it keeps it additional insulation layer. So, and basically it's a security barrier, because if people are getting into unit, you want to extend the time that I need to get into the hardware. And better insulation, but also you don't see the unit, it's in the ground, only the lid. And we're going to paint that green in the future. And it's compliant with ISO certification. So this next version that we had, the left side, that's what's inside that box. And it's not easy to get in. You really need power tools, and also it's locked from the inside. So even if you unbolt all the bolts on the side, you cannot open it. Okay, so we have extended the time that people can get access to the hardware. We made it almost impossible with normal tools, and extended the time to 20 minutes with power tools, if you really want to. But the next step is then detection. So we can have capacity sensors that if you touch the unit, it will detect it. We can have vibration sensors. And if you're going to build it your own, yeah, a Raspberry Pi is great to use it, Arduino, but also if you want to do it yourself, you could use microcontrollers, for example, that processor, and below there's yeah, the setup that you can use to get started with this. But yeah, that's great. Oh, yeah, it's great because the time we live in, 20 years ago, you would be building from scratch your own yeah, embedded system, and now you can just buy it. So if you want to get started, it's very easy now, and then you can iterate and build your own when you go along. And there are like 3 protocols. If you know those, yeah, I2C, one wire, and SPI, then you basically set and can do like hundreds of different types of sensors. Okay, the unit is in the ground, it's secure, it has a layer, it's locked from the inside. If somebody only looks at it or touches it, you know it. You can have a camera outside with a telecom network. And the next one is incident response. So if you place it on your own property, it's basically theft of your property. So you can call the police or local security instances. Yeah, local security services. So the next one is cooling. Are there any questions about this topic? Yes.
Let's assume that there is somebody trying to physically steal the unit. And also have some digital measure in place that will fill it with liquid or disable it in another way.
Yeah. Yeah, yeah, that's a good question. So the question was, do you have digital systems in place to prevent theft or make it harder? So yeah, of course, data is always encrypted in flight, but also on the storage. You have specific cards that remove the private key if there's an entry. I went to Dubai and they had NVMe cards that could explode. So you can go really far with self-destructing.
It's like with the shops when they have an ink pattern on it.
Exactly. That would be great. Yeah. So yeah, the ink patterns they have with banks. Okay, let's go on with the cooling. So if you compare to air, you need a lot of components. Like you have your server room, you have cold and hot air that needs to be circulated. Then it needs to be transported to a chiller. From the chiller it goes to a condenser coil. But you see there are a lot of components, and I've built it myself because I had a startup and I needed a lot of cheap computing power. I did the calculation, if I go to the cloud, it would have been 5 times more expensive. And if I just bought the hardware, I could use for 5 years, and it was much cheaper. But yeah, it's not really professional, and also there's a difficult thing because if you cool with air, you need to look at temperature and humidity. And if you look at efficiency, so I built the next one. If you look at efficiency in the winter, you want to use the air from outside, so you don't have to cool, but you need to regulate the moist, and then you have also dirt coming into the unit, and that makes it very hard to do so. And it's frustrating. So I thought that there must be a solution to do this. Like it's cloud or on-premise. Like, is there no middle ground? And that is something that frustrated me. So I came along with immersion cooling. And yeah, probably a lot of you already know about immersion cooling, but it's basically a liquid, a oil. You can use mineral oil, but there's contaminants in it, and you want to use the GTL. It's based from natural gas. It's built, and like here I have a representation. So this is the oil and the Raspberry Pi, and just put it inside, and then it runs no problem. So if you want to do this, like here is your container with oil. You take a server, remove the fans, remove the paste, the thermal paste between the processor and the heatsink. That's more on that next slide. And basically the oil comes here, it gets heated, and if oil gets heated, it expands, gets lighter, and it goes to the top. There you take the oil, it goes to a heat exchanger, and it goes back. And the heat exchanger, there's where the oil is cooled with just water. But the great thing is from here is that normally you have heat that you need to transport in the sense that you have air, but now you have water. That's great. With warm water you can do a lot of useful things. So I also built this one, a prototype. And yeah, so this represents the tank, the pump, some electronics, and then here a water container and a evaporator system. So this works pretty well. It looks complex, but it was very easy to maintain, especially maintaining. So if you look at the same pictures, you don't need the circulation system for inside your server room. Those you don't need, but also you need less pumps. You don't need a chiller. So yeah, less is in general better. So that's why this is a good route if you want to use cooling. But also there are some downsides, and that's like the thermal paste that you have between the CPU and the heatsink. It will etch away. The oil will remove it. So you're left with, after a month, you're left with nothing. So you can apply indium, but it's quite expensive, but also graphite pads, but then you have a performance loss. And also a funny thing is the rubber. If you have capacitors on your main board, the motherboard, they pop, they came loose because the rubber will expand with 30%. And they're against the PCB, so they will just automatically disassemble themselves. So it's quite useful if you do that. But cables become stiff, really, they become sticks. Fiber optics are problematic, and oil will get anywhere. So yeah, if you look at parking, it's there. So this or next iteration, it's already looking more like a finished product. It's basically a box that you can place anywhere. You put fiber in it, electricity, and hot water comes out. So yeah, we already talked about the heater. Servers are basically heaters. But how do you dissipate the heat? Are there any questions about the previous topic? Yeah, definitely. Intel is providing extended warranty for their processors, so you really, and this is like necessary, right? If you look at AI, where you have like 1 kilowatt chips, where we're heading at, you need to have microchannels. You're not going to do it with air, so we have to use liquid for like high energy systems. But yeah, the industry is working towards this, because also if you look at performance, oil is much better in extracting heat from your system. So thank you for the question. Yeah, and then if you look at the temperature, so you have the thing in the ground, it's secure. You have built it with oil, for example, and you have the heat. What are you going to do with it? Well, low temperatures between 10 and 30 you can use for aquatic ponds. So for fish or that kind of stuff, but also underfloor heating is very useful. It can only handle 39 degrees. You don't want to go higher than that. So that's like great low temperature applications. But also if you look at high temperature, that's even better, because you can make things smaller in size. For example, if you have a heat dissipator, you can maybe half or 1/3 of the size. But also you can use for showering or swimming pools, industrial. So yeah, if you are making this, low temperature is fine, but if you can get to 60 or even higher, that's even more amazing. Like 60 is the boundary that you want to cross. Then it's almost useful for a lot of applications. And if you look at the temperature, so silicon will go to 105 Celsius max. So that we know like that's the upper limit. And if you look at the consumer or server grade systems, they go to 95 maybe. So there's just a physical limit. You cannot go higher than that. Well, maybe with innovation, but for now. So we need to look at like, yeah, how are we going to increase the water temperature or the oil temperature? Because yeah, we want a high temperature. So there are so different things, and that is terminal resistance. So if you have a heat source that's 95 degrees, and you have a low terminal resistance, there's like a small delta temperature between the oil, the coolant, and the heat source. So yeah, the smaller you can get that, the better it is. So you can delit your CPU. You're talking about in the introduction with me. In the past, that's like more done, but yeah, you lose warranty, and that's maybe a con. And they're looking at microchannels. So with AI, can you cool in the chip instead of against it? So there are some innovation. This where you want to innovate on the reducing terminal resistance. Like, yeah, we talked about air, the types of heat sinks. That's like pretty familiar. You can immerse the thing in the oil and remove the fans and use natural convection. Then you get a temperature between 30, 50 degrees because, yeah, everything is in one basket. So you cannot, take the heat from one point. It's radiated to the outside. And that's why water blocks can get a higher temperature. So you can put it on the chip and you get 50 or 85, depending on your innovation. But you're losing half of the heat because the memory and other modules also dissipate energy. You won't capture that. So there's some troubleshooting you need to do there. So yeah, how do you dissipate the heat? So you have to dig in the ground, and now you have the hot water, right? Where can you dissipate it? Well, there are these kind of buffer tanks. They're made for sustainable energy. For example, a solar collector on your roof that heats the water. You can connect it to those kind of things, but also your cloud unit. If you have a heat in your house, for example, floor heating, underfloor heating, where it goes to your heater and through your house and back, there you can put a heat exchanger. So it preheats the water before it gets to your primary heater. So it doesn't have to start when it isn't necessary. And of course, if it isn't possible and you want to be able to always run your compute, you have to dissipate the heat. But that's what's being done right now with most of the heat. And then we're going to talk about the hardware. I think we're good on time. Any questions about this previous topic? No? Okay. So the hardware, basically, when we talk about servers, we talk about managed servers. So you have a compute unit with a remote control unit. Because if you only have the compute unit, you talk about consumer hardware. If you have a consumer hardware with a remote control unit, then you have like a real managed server. And I made this talk from the perspective that you're going to do this yourself, maybe beside your job if you're up to it. And you don't want to spend thousands of dollars or euros on official servers. They're expensive. So one thing you can do is just buy a server, 5 to 1,000, maybe 2,000 euros, depending on your needs, and then have a KVM. So not a software KVM, but a keyboard, video, and media device that will connect to your server. And from that, you can control the BIOS, the keyboard, and the mouse. So basically, you have the same capabilities as a official server, but for much cheaper. Yeah, of course, you need to look at ACC if you're going to do this for clients. It needs to be secure and reliable. And you need to think about mean time between failures. But that, it depends on your use case. So if we talk about the KVM, there's a pretty useful thing you can use out of the box. That's PyKVM. It's basically a Raspberry Pi with a head on it. and yeah, it has all the stuff, so you can basically connect it and you're done. That's the easiest. There are also other closed source KVM solutions, sorry, or you could build your own. Only one advice: always use a isolator like the PC8017. That is like if you make a short circuit in your electronics, you will blow up one side of the chip, and the other side that's connected to your valuable hardware won't be impacted. So yeah, any questions? Great. Then we're going to talk about the architecture. Yeah, this for me was this was the most fun part because I like infrastructure and building things with configuration management. So yeah, there are different setups you can do. You can have, of course, your grid and your local green energy because we want to be sustainable and more efficient. You can use a UPS for if power fails, but also, yeah, are you going to use one cloud unit? For example, one of our customers use one cloud unit, but yeah, one is none, right? So if it fails, then you have problems. So what you can do is, if you're building your software stack, so why not move it to the cloud? And that's what we have done. We've built a cloud unit itself and a software layer on top of it. And we don't care if the software layer is running in the cloud, by Azure, AWS, or anything, or on our own hardware. So one thing we do is, for example, this night, I moved the full stack to AWS. I can now put out a unit, replace the hardware, and then place it back without any interruptions or any obstructions to the customer. So yeah, this is something you can think about. It's also one other solution we've built is that you have the cloud unit because it's locally. Things will break, and even if you have a hardware like real server hardware, you can have your motherboard, 2 CPUs and memory, but still at some point it will fail. So yeah, if you take that in consideration, you want to put the reliability and the availability in the software itself and solve the problem there. So what we've done is we've built in Azure a service bus queue where they can scale with function apps like they do normally. But if the cloud unit is available, it will also spin up function apps and it will descale in the cloud. So in the case that something happens to the cloud unit, the power switch is disrupted or the fiber is damaged, it will automatically go to the cloud and there's no impact. Yeah, this is really fun to think about, and you can think of different scenarios, how you want to do this. Yeah, how does a cloud unit look from the inside? There's a gateway. You can use like Cisco equipment or just a server with Ethernet ports. We've chosen the latter because, especially with AI, and you don't know what software-defined infrastructure, you want to be flexible, and that's what we've chosen. But you can also use other stuff. So your fiber comes into the unit, it goes to the compute units. So we have between 8 and 16 compute units in one cloud unit. And then there's the out of band module, like the KVM where we talked about, that you can, even if the fiber is disrupted, you can still access the servers through the phone network. And you really need that to maintain the system. You don't want to open it every time if something breaks. So the last one, yeah. Yeah, so we're experimenting with that. We've made a incision into the lid and placed the antennas there. And under we have another stainless steel layer. But that's maybe useful in urban cities. But for remote, we have like a standalone antenna that is mounted on the unit itself. But that's of course the challenge. Yeah, you have a Faraday cage basically, so nothing will go out of it. Yeah, if we look more specifically at the software layer, so we talked about the gateway. API request goes to the gateway. This is just how we've done it, right? You don't have to do it this way, but maybe it inspires to do it not this way or do it this way. So we run FreeBSD on the gateway. We have there our data. We use ZFS as a file system. The OpenBSD we use for the out of band management modules. Yeah, it's just I think it's quite secure and low maintenance, stable. So we want to have the most stable system running on there and low in resources. 3, that's the FreeBSD Linux. So on the compute node itself, so the 8 or 16 servers on the right. There we have FreeBSD or Linux, and on Linux we use LXC as container management system, and on FreeBSD we just use Jails to do pass. Sorry.
You've got FreeBSD everywhere, both for the
Yeah, so myself, I love OpenBSD, and I'm quite in favor of it. But it has its limitations. Like, you can run VMs with only with one core, and FreeBSD, of course, is used by Netflix, so the network stack is really good. So we try to apply, the systems where it makes sense. So for the gateway, it's FreeBSD for its performance networking and file system. OpenBSD, it's secure, lightweight, and easy to manage, stable. And so we try to take the cons and place them on the right places. But it could run FreeBSD, why not? But but you can do it yourself, whatever you want. So and then FreeBSD, the Jails containers, LXC. That's what I. Pipelines. Point 4, thank you. So you have a gateway and the nodes, right? And what we want to do is if a workload comes in, we want to utilize one node 100%. And then if it's going to 100%, maybe 80, spin up another node and have the other one just off to save energy, because we want the most sustainable and green cloud unit. And the task scheduler just looks at, okay, what's your resources like and what's your availability? Okay, then I'm going to spin up a new system or place a compute workload on the first server. Exactly. More like orchestrating, yeah. And the last one, the software, and this is like, where you can, the thing most of you do already right now. So you can host this yourself and build your own software stack. Use subjects maybe for monitoring, run Kubernetes or Elasticsearch. Just put some ideas here. Nextcloud, that's something we're looking at in Germany. They want to maintain and control their data. So an on-prem solution that's fully managed by us. We supply Nextcloud, where you have a full office suite that you can use, and you know that your data is secure and low latency for your office. The other one, depending on OpenFast, also a great. Another one, it's a framework where you can just deploy. I think it's based on Kubernetes, where you just run fast. We've chosen to implement our own, but Yeah, there are some great solutions, especially, and I think like I have a background in electronics, and from where I worked was like, yeah, we design our own PCBs, our own software, and we keep it for ourselves. And that's great. And that's why I switched mainly to IT, is yeah, everybody just gives it away for free. And if you want to bootstrap a new idea, this is just like, yeah, even if you do want to do it yourself eventually for optimization reasons, just to get started, you can use one of them. So that's great, yeah. And without open source, that would not be possible. And this is, yeah, hybrid cloud you can use. So that's what I said before. For example, you can use the stability and availability of the cloud itself as a service bus queue and put in your tasks, and then have just units that look at the queue, and when there's something to do and they're available, they just look at the queue and take work from it and tasks. That's great, and that's more like a hybrid cloud. Or, and that's the last one, that is, yeah, the full stack the full stack implementation. So Azure and AWS provide Outpost or HCI, where you can run like a new availability zone on your own hardware, but I think it's around 10 euros per core that you pay additionally for running their stack. So, but yeah, maybe for government where they have some compliance or that kind of reason, cost is not really an issue, and you're even like 20% cheaper or more cost effective than the cloud. So yeah, maybe the 10 you're at the same cost eventually with all the features of the cloud. And one of the bonus slides, that's this. Yeah, we talked about the different layers, and I also divided them up, the marketplace. So let's say you want to do green software, but don't want to spend on the lower layers. For example, yeah, the immersion fluid, you can buy it at Shell, or engineered fluids. Maybe that's enough for you. Maybe you want a tank. So you can buy Submerged Peritas or Exora. You buy the tanks and you buy the fluid, and then you have that solution. Of course, you can look at green software, how to optimize and reduce resource usage. Those are two great sources. And if you look at the sustainable cloud, there in the Netherlands, there are now two companies, We, Green Compute, and Leaf Cloud. So if you want to just run by what AWS is providing, but yeah, just use another cloud service, then you can look at those companies. If you want to use edge computing, so for example, water treatment facilities or archive processing, maybe cold storage, and you want a solution that's ready to go, fully managed on the edge, then you can use also Green Compute. But yeah, that's I think that's it. Thank you.
Any questions? Yes.
Thanks for the talk. It was very nice. Do you have any like specific specs about sort of like the product that you're providing right now, like in terms of like how much hardware, how many watts do you get out of that, and like if you something like, yeah, how much can you get out of it? And
yeah. Oh, sorry. So the scale depends on what you want to build. For us, we decided to use 3 kilowatt of energy per cloud cassette, per cloud unit, you could say. So depending on your workloads, it will be between 8 and 16 servers. We go a little bit higher, but our vision is that we want to deploy thousands of those units all across the Netherlands. And if you have a house, 2 square meters of space left, then we can put a unit there in the ground. And with that vision in mind, you want to be able to just plug it in the wall and have it working. And 3 kilowatt is just the max at a normal 16 ampere 230 volt group. So that's why we decided that if you want more, you just put another one next to it on another group. But if you design this more for a business that does not have those limitations, that does like high power, then you can build larger. But for us, it's 3 kilowatt per unit, and it also produces 3 kilowatt of heat.
Yeah, if you would design this for for a business, would you not? Why would you put it in such a sealed box? I mean, most businesses have office space where they can have a room to fill with equipment, and then just lock the door instead of putting sealed boxes under the ground.
Yeah, exactly. So that's what I said in the beginning. If you think like I only need the sensor layer for securing your on-premise server room, use that. From our perspective, our vision is that we want to have thousands of those units all across the Netherlands. And if we need to knock on the door, the server has broken, can we please get in? Then it doesn't work, it doesn't scale. So for that reason, the lid, it comes automatically out of the ground. So from the office, we unlock it, then you can open it, or field engineers goes to the unit, connects with Wi-Fi, fills in the code for auditing, and then the thing comes out of the ground automatically, and the lid is shifted away and the hardware replacement. But mainly for security, because normally you have the building as security perimeter, right? And we don't. So that's why the focus on security.
It looks to me that the overhead cost of such a small unit is too large. If I would compare everything which is in the box compared to the 16 servers in it, it seems to me a huge overhead, and even maintenance would be much higher. The large data centers even don't switch any servers or components. It's a complete rack because of overhead costs. Your overhead costs would be enormous, I guess.
It's quite surprising. So if you divide, for example, the hyperscaler, that costs like around 2 billion to build, divided by the megawatts or kilowatts of power, things like that. Okay. Or kilowatts of power. Yeah, you can do the calculation. It's surprisingly, you're paying surprisingly a large sum of money for your compute in the cloud. And that's why, if you just lay normal prices and do it like this, it's manageable, it's doable. It's much more, you would be surprised. That was my assumption also. And when you do the calculations, it works out. Yeah.
More questions? Yes. Last question, I think.
There's water coming out. That's hot water. I assume you also think about heat pumps, or water-to-water heat pumps to even have more efficiency on the water output.
Yeah, well, yeah. So we try not to use those kind of solutions because it is one solution, right? So that's great, but we would prefer to hire the heat and have less components, because again, we think about scaling. Also your argument, you have thousands of units all across the Netherlands, so you want to keep it simple, scalable. But yeah, like if you have such a system as that we have a cloud unit, or you've built your own, of course you can put a heat pump beside it if you want more efficiency or more heat. But that's, you can do that. Yeah. But from our perspective, we try to keep it so simple as possible. Yeah.
Well, Nick, thank you very much. That was most interesting. It's a thing that I actually never thought of. So, and I think most of us that. We wish you lots of success. We thank you for your talk, of course, and maybe next year you'll come and present new results. That
would be great. Thank you for being here.